In this video, we're going to talk about the idea of limits. Our objectives are going to be to introduce the concept of a limit, to calculate average and instantaneous velocities. Those would be rates of change, so an average rate of change and an instantaneous rate of change, to calculate slopes of secant and tangent lines, and to identify the equivalence between instantaneous velocity and the tangent line. These topics come from sections 1.1 and 1.2 of the textbook. So first, let's look at a definition of the tangent line. It's a straight line, like all lines, but it's a straight line that just touches touches the graph at only one point. A graph, for example, if we have the graph f of x here, just going to draw something like this. This is f of x, and we're going to pick a point of tangency over here. I'm going to try and change color here so that you can see the difference here, that the slope of the curve and the slope of the line will be the same there at that point here. A f of a, and this x equals a. Lots of times we'll actually call that point there C, but this line here is going to be y equals mx plus b, right? And it's going to have the point A, f of a, on it. All right, let's go back to our definitions here. So when we find the slope of a tangent line, that's a key concept in calculus, and it leads us to our first major discussion in calculus. So we define tangent lines carefully in the book. For the moment, though, imagine zooming in on the point P here on this function. As you zoom in, the curve appears more and more like a line passing through P. This line is the tangent line at P because a smooth curve approaches a line as we zoom in on one point. We'll talk about this later when we talk about something called linearization. A smooth curve is said to be locally linear at any given point. So how do we derive the equation of this tangent line? So we use secant lines. And this is going to look very familiar because secant lines are going to have to do with the difference quotient. So remember, the to find the equation of a line, we need either slope and y-intercept, or we need point and slope, or 2 points will be enough here to get us the slope, and then we can use one of those points. So let's go ahead and look at what a secant line is. So it's any line that passes through exactly 2 points on a function. And we're talking about locally. It may go through other points later if the curve goes up and down a lot, but let's draw this function here, f of x, and we want a tangent line we've already talked about here at this point here. It's our tangent line. But let's make a secant line now. Same point there, but let's pick another point up here. And 2 points determine a line. And as I bring this second point closer and closer and closer and closer to the original point, I'll get many secant lines that will come in closer and closer and closer to this tangent line is going to be the idea. So I can use the idea that 2 points determine a line and find the slope and squeeze in on the slope of that tangent line that way. So let's finish up my labeling here. This point up here is going to be b, f of b. This point here is a, f of a. And we have y equals mx plus b, this b not related to that b. And so let's find the equation of a secant line, considering the function s of t equals negative 16t squared plus 96t. If I factor this, this is negative 16 times t squared minus, this is negative 16t times t minus 6 is what that is. So it's going to go through 0, 0, and it's going to go through 1, 2, 3, 4, 5, 6, 0. That's going to give us a maximum value probably at t equals 3. So let's just check. Negative 48 times negative 3 is 144. So 3, 144. I think that's going to be my vertex here. Negative b over 2a is yes. So there's my vertex, and it's coming here. turning, going down there, should be symmetric. I may not have drawn it completely symmetric, but that's the idea there. And so we want to use one something and 3 144. So when I stick in 1, I get -16 times a -5 is a positive 80. So 180. That's going to give me a secant line that's going to go through those 2 points. And it's going to have a slope of y2 minus y1 over x2 minus x1 is going to be 64 over 2 is 32. And we're going to have y minus y1. So y minus 80 is equal to 32 times x minus 1. Y minus 80 is equal to 32x minus 32. Y is equal to 32x 80 minus 32 is 48. So that's going to be a 32. Now this is not actually x values, these are t values. So we're going to change that variable there because this is s of t. So that variable should be s for position. S of t is equal to 32t plus 48 for my secant line there. So now let's generalize this concept for any 2 points P1 and P2 here, and we can get lots of secant lines. We can move P2 closer and closer to P1 here. And we're really interested in getting this tangent line, though, that's right here. So if point 1 is going to be A, f of A, and point 2 is going to be B, f of B, then our slope is going to be f of B minus f of A over B minus A, and that's going to be my average rate of change. Which is going to be the slope of my secant line. If we move P2 closer and closer to P1, our slope of our secant line is going to get closer and closer to the slope of our tangent line. So using the slope of the tangent line to a point to determine the limit of a function at that point, they're going to have the same behavior locally at that point. And I can show you this video, share that on my YouTube channel as well. But there's just one that we would show in class there to show you that visualization of actually moving this point closer and closer and closer and closer to this point until we actually get the secant line becomes the tangent line. So let's go ahead and look at how we do this and why do we care, consider f of x is equal to x squared plus 5 based off of the parent function y equals x squared, right? At the point x is equal to 1. So I'm going to 1, 2, 3, 4, 5, and it's quadratic. Not going to draw it perfectly, but it's going to be something like that because of transformations. And at x equals 1, we have 1 plus 5 is going to be 6. We're going to be somewhere up here that we want to find that tangent line right there. Well, let's go ahead and let's use f of x equals x squared plus 5. And we want this tangent line y equals mx plus b. But we can't get that because right now we only know how to find the equation of a secant line. So we're going to pick a somewhat close point there. That's going to be a b f of b, like that. So the x value to the right of x equals 1, and any point to the right. So that x2 is going to be b, and the y value will be f of b, and the slope is going to be the slope of the secant line using, this is 1, and when we stick 1 in, we get 1 plus 5 is 6, and this is going to be b f of b. It's going to be f of b minus f of 1 over b minus 1. And so f of b is going to be b squared plus 5 minus 6 over b minus 1 is b squared minus 1 over b minus 1. And that's going to be b plus 1 times b minus 1 over b minus 1 is equal to b plus 1, as long as b is not equal to positive 1, because we need to have a slope. We can't have a line if we're just simply at the same point there. However, we will play a trick here in a little bit and say, well, what happens as we get closer and closer to b being 1? So m is going to be equal to b plus 1 is the value of the slope of any secant line between 1, 6 and b f of b. This m value is the slope of the secant line starting at 1, 6 on f of x and crossing f of x through x equals b. Notice here b greater than 1, and this is any x equals b with b greater than 1. So we can actually simplify this one step further by factoring the numerator and canceling out like factors. We did that, numerator and denominator. Now visualize the secant line rotating towards x equals 1 to become a tangent line at x equals 1. So like I said, imagine this point coming closer and closer to that point, to where b is getting closer and closer and closer to 1. So as x equals b becomes closer to x equals 1, eventually b equals, in quotation marks, 1, that we can't tell the difference visually anymore. the value of b equals 1 causes a problem in the original expression for the slope of the tangent line because we will be dividing by 0, right? Even though we canceled it out. So let's look again here at m equals b squared minus 1 over b minus 1 is undefined. At b equals 1, we get 0 over 0, which is something in calculus that tells us that there's probably some algebraic simplification we can do with the limit. So we do some algebra, and we get that m is equal to b plus 1 when b is not equal to 1. Using that algebraic simplification, we obtain the actual slope of the tangent line to f of x equals x squared plus 5 at x equals 1 by saying we're going to ignore this restriction and try and stick 1 in for b there and say m equals 1 plus 1 equals 2. And we get the slope of the tangent line to the graph of x squared plus 5 x equals 1 is 2. Some more generally, the rotation of the secant line to the tangent line in this example is very basic. Look at the illustration here. Point Q, as they call it here for the second point, moves along the curve towards point P. As B approaches 1, the secant line rotates towards the tangent line. As B approaches 1, the secant slope approaches the tangent slope. So as B approaches 1, m equals b plus 1 approaches the tangent slope. As long as b is not equal to 1, thus the tangent slope is 1 plus 1 equals 2. At first in calculus, this is the approach that we'll use to find the slope of a tangent line. But what we've really just shown you is the concept of a limit, because we had a number that we weren't allowed to have, but we got really close to it. We needed 2 points to have a secant line, but we got the 2 points so close together that they essentially became 1 point, and we figured out what was happening at the curve and the tangent line at that 1 point. So in calculus, we use the following notation to describe the slope of the tangent line as follows. The tangent slope is equal to the limit as b approaches 1 of b squared minus 1 over b minus 1. This is just using our previous example, is equal to the limit as b approaches 1 of b plus 1 times b minus 1 over b minus 1, and those will cancel because I'm not getting 0 over 0. I'm getting a number close to it, is equal to the limit as b approaches 1 of b plus 1 is equal to 1 plus 1 equals 2. So we're going to be talking about the slope of the tangent line is going to be called a derivative here. And that's going to be our big concept in chapter 2. So let's go ahead and we just did this work right here. That's what would go in that box there with you try. So we could also say limit as b approaches 1 of b plus 1 equals 2. In general, we write the limit as x approaches c of the function is equal to L, where L is a finite number. It cannot by definition be infinity or negative infinity. It must be a number L that's a real number right now, since we're only dealing with real numbers. So limit as x approaches c of g of x equals L. Using slopes of secant lines, let's make a conjecture about the slope of the tangent line, and we'll go ahead and use that information to make a table of values here for the tangent line for f of x equals 9 sine x at x equals 0. So let's think about what sine looks like here. It's going to come up here, go down there, but we're interested at 0 right there. This point here is 0, 0. The tangent line is going to be something like that. And we're going to have to figure out what's going on with that slope there. We can draw some secant lines here if we want to, just put a generic point over here that we're going to call b, f of b. Actually, let's get a point that we know what it's going to do. So at pi over 2 over here, where it reaches its maximum here and comes back down, this point here is pi over 2, 9. And this point here, pi over 4, is going to be 9 root 2 over 2. And we have pi over 6 is pi over 6, 9 halves. And we have 0, 0 there. So we can have several points there. So let's look first here. F of 0 is 9 sine of 0 is 9 times 0 is 0. We'll be using that every single time. F of pi over 2 is 9 times sine of pi over 2 is 9 times 1 is 9. That's where I got that from. F of pi over 4 is 9 times sine of pi over 4 is 9 times square root of 2 over 2 is 9 root 2 over 2. And f of pi over 6 is 9 times sine of pi over 6 is 9 times 1/2 is 9 halves. That's where I got all those numbers from. Now, going to choose x equals pi over 2 for our first secant line here. And we're going to be looking at the interval from 0 to pi over 2. So the slope of the secant line is going to be f of pi over 2 minus f of 0 over pi over 2 minus 0. And that's going to give us 9 minus 0 over pi over 2 is going to be 9 over pi over 2 is 18 over pi, which is about 5.73. Let's go ahead and look at my intervals and my slope of my secant line. So we just started off with 0 to pi over 2, with this being my A and this being my B, and we have 5.73. Let's go ahead and change that from 0 to pi over 4, and we'll go ahead and let you calculate that here. And I'm just going to tell you that you'll get about 8.10, then 0 to pi over 6 is going to be 8.59. Then I want you to go ahead and stick in something ridiculously small, like 0.001 there. And we're going to see that this gets to 8.999. And so we're probably going to say here, let's go ahead and to x equals pi over 4, 0 to pi over 4, f pi over 4, we said was 9 root 2 over 2. So our slope would be pi over 4 minus f of 0 over pi over 4 minus 0, 9 root 2 over 2 minus 0 over pi over 4 minus 0 is 4 over pi times 9 root 2 over 2 is 18 root 2 over pi is about that 8.10 I told you about. And the third one that we did here, x equals pi over 6, makes my interval here like this. F of pi over 6 is 9 times a half is 9 halves. So slope is f of pi over 6 minus f of 0 over pi over 6 minus 0, 9 halves minus 0 over pi over 6 minus 0 is 6 over pi times 9 halves is 27 over pi is about 8.59. And then number 4 here, when x equals 0.001, you have the interval right? And you're going to need your calculator for this for radians, but f of 0.001 is equal to 9 sine 0.001. So again, calculate in radian using radian mode. So that's 0.001 radians that we want there. And that's going to be 0.008999985. And so we have m is equal to f of 0.001 minus f of 0 over 0.001 minus 0, 0.00899999985 minus 0 over 0.001 minus 0. It's going to be 0.008999999. 1, 2, 3, 4, 5, 6 nines. 6 nines, 85 over 0.001. Move 3 decimal places to the right. 1, 2, 3. 1, 2, 3. So this is going to be 8.9999999. So 1, 2, 3, 4, 5, 6. 4, 5, 6. 8, 5. And that's about, we're saying 8.999. This is just about 9 actually. If we want to round it to, we'd have to round it all the way down here to get something that's not 9. So we can do that 8.9999999, 1, 2, 3, 4, 5, 6, 7. Let's come back up here to my table and do that. 1, 2, 3, 2, 3, 4, 5, 6, 7 decimal places is where we'd have to go there to not get 9. And so our conjecture following the pattern in the table is that m, our slope of our tangent line, is going to be 9 slope of the tangent line at x equals 0. And it is. We'll find out why it is as we go further into calculus. Let's keep going here. Average velocity and instantaneous velocity. So physical interpretations, the slope of the secant line can be interpreted as average velocity or average rate of change. And the slope of the tangent line can be interpreted as instantaneous velocity or an instantaneous rate of change. Things you can think about, like if you have speed enforced by aircraft and you have a line here and a line here, and I give you the total distance d that you traveled from time 1 to time 2 that I measured with the stopwatch, and I do that your v is equal to delta d over delta t, like that, that's an average rate of change, where I just have a fixed distance and I know you're changing distance over your change in time, but I don't know exactly what speed you were going at any moment in time. Instantaneous velocity, we're going to use something like radar or LiDAR or whatever, and we're going to get these really tiny incremental measurements that we're going to figure out this distance over this time, and we're going to do it with physics, with Doppler effect and phase shift and all kinds of fun stuff from physics that you can talk about later, but we know based off of that what that change was at that instant in time, because we're sending out so many signals in such small time intervals that we know what happens basically at every instant in time because of this limit idea. So using average velocity to find instantaneous velocity, the function s of t equals negative 16t squared plus 96t. We used that one before. Can be used to model the position of a rocket after it's launched vertically into the air with a speed of 96 feet per second from ground level. The position s is measured in feet. So s of 0 corresponds to the ground. Make a conjecture about the instantaneous velocity of the rocket at time equals 1 second. After it's launched, use the intervals of t given. So, and I'm just going to fill these in for you. You can go ahead and work through this here, that this is 32, 48. This is one of the ones we're going to find. Sorry, this is 48. This is, we might want to find 1, 3, for example, would be 32. We might need that one. 56 is here. 62.4, 63.84. These are all in feet per second. And this is going to be 63.984 feet per second. So our conjecture about the instantaneous velocity here, as we get closer and closer and closer to t equals 1, is we're getting closer and closer to 64 feet per second. Again, I did all this in a calculator ahead of time. So let's go ahead and show you what I'm talking about. That here's 1, 2, 3 was my apex here. Was it 144 if I remember this correctly? And came 4, 5, 6, came back down to the ground there. Starting at 0, 0. And we had 3, 144 up here. But we're interested in what's going on right here, what that velocity is right there when t is 1. So s of 1 is equal to negative 16 times 1 squared plus 96 times 1. It's negative 16 times 1 plus, it's going to be negative 16 plus 96 is 80. So we have the point 180 is going to be one of my points that I'm going to use. That's always my left point for this example. And then I can use the interval from 1 to 1.15. X equals 1.15. I get S of, this is actually T equals S of 1.5 equal to negative 16 times 1.5 squared plus 96 times 1.5 is equal to 108. So my M is going to be equal to F of 1.5 minus F of 1 over 1.5 minus 1 is 108 minus 80 over 1.5 minus 1 is 28 over 0.5 is 56, and these are feet per second. We're going to have to do the same thing here. This is T. This is, just use your calculator, 80.6384. And so my M is going to be 80.6384 minus 80 over 1.01 minus 1 is 0.6384 over 0.01. It's going to be 63.84 feet per second. And we've got 3 here is 1 to 1.001. T is equal to 1.001. S of 1.001 is, using your calculator, 80.064. So M is 80.064 minus 80 over 1.001 minus 1, 0.064 over 0.001. And more precisely, it's not this, it was 63984. So 63984, 3984, 3984 is going to make this, move this 3 places to the right, is going to make this 63.984. And so we're getting closer and closer and closer in on 64, like we said. So that's it for this video. We'll come back next time and we will talk about the limit of a function. So we'll see you for the next video.